Hey Miguel, go ahead and ask me any questions if you have any before we get started. We still got 7 more minutes, so you got plenty of time. Uh, but you can type in the chat, you can type a question, or you can say it out loud if your speaker works. Or you can just hang out and wait. I'll just be sitting here working on my notes and stuff. Giovanni, if you have any questions, feel free to ask. I'm just sitting here prepping for class and looking up some stuff. Thank you for go ahead and type in your first and last name. You can do the same thing, Miguel, if you'd like. Hmm. Type that into the chat as our roll sheet, in other words. Lillian, type in your first and last name in the chat if you'd like for your role, for the role today. Of course, you can do it later. It's not a big deal. I just want to make sure I reminded you. You can also ask me questions. Looks like I got about half a minute. Actually, scratch that. The minute's over. So it is actually time to start class. Anybody have any questions before we get cracking? We've only got 4 of you guys in here, so we're a little underpopulated, but that's okay. I promised everybody I was going to change the dates, and I thought I did it on the weekend before I left, on before Friday, anyways. But evidently it didn't take, or I didn't do it, or I did the wrong class or something. So I just fixed the due dates for the homeworks, not ago. So everybody go ahead and check in Pearson to see the new due dates for the homeworks. Kind of hoping we've got some absences because maybe people are trying to rush to get their homework done. So hopefully that'll bring them in. Yeah. There I go yawning again. I don't know what's going on. So anybody have any questions before we get started? As you're logging in, make sure you go ahead and log in and then type your first and last name into the chat. So I'll have you for roll. And then we're going to go ahead and get started. No questions? All right, well, let's go ahead and get started. I had a couple problems of the general projectile motion type problems to work with you guys, so I thought I'd go ahead and do that. And that'll finally finish up chapter 3. There is a relative velocity thing, and I'll just give you the equations of that and tell you sort of how that works a little bit, but that's about all we're doing for that part of chapter 3. As the semester progresses, we'll occasionally use that. You'll actually see a few problems, but I think with the little intro that I give you, that should be more than sufficient explanation of the relative addition, velocity addition problems. So I'll ask one more time before we get started. Anybody have any questions before we get started? All right. Well, looks as though no one said anything. I'm checking the chat real quick to make sure nobody posted anything there. So yeah, that looks like we do not have it.
Oh, Professor?
Yes, go for it, Alex.
Yeah, I just had a question about it was just one of the things on the test, which maybe I'm just spacing on. I think it was saying like if the acceleration is 0, like what is the velocity? Or like what can the velocity be or something? And I think I put constant. But I think they were looking for the answer to be like velocity is 0.
It can be constant, but it can also be changing. For instance, and they said when the acceleration is 0, is that what they're asking?
Yeah. It's like what's velocity if the acceleration is 0?
Well, yeah, that's probably fair. I'd actually have to see the actual choices,
Yeah.
to know what the best answer is. So I'm not really sure. I'll look. I got your name. I'll look at your test and see if I find anything about that. I'll also say that 2 students came to me today and they had a problem related to the mean free path. And I promised that wouldn't be on there. So if you happen to get a test that had mean free path on, I'm just going to give you full credit for that because that wasn't supposed to be on there either.
Okay.
Of course, three attempts. So hopefully within one of those 3 attempts, you get.
Yeah, it's not on there. Yeah.
Okay. All right. So I'll check yours out and see. I actually had one of the mean free path questions that someone had one where they didn't give us the actual radius of the atoms or the diameter of the atoms, so it was a little bit more complicated. But
All right, cool.
yeah, I'll look at your question and see what I can find out, and I'll let you know what they really meant by that. And
Okay.
I might make it something where I'll tell everybody, that way everybody benefits from it as opposed to just the one person that asked. Okay.
Okay, sounds good. Thanks.
All right. Thanks, Alec. Appreciate it. Okay, so the problem I had decided to work for you guys was a typical problem that I do as a physics demo. And of course, with, social ills as they are and, bunch of mass shootings that occur and that sort of thing, We've tried to refrain from using words like shoot, especially when I go to do presentations to middle school and elementary school and stuff like that. They just don't want you using the word shoot. They don't want you using the word gun, all sorts of stuff. So we transformed this presentation that we had from shoot Barney to throw the ball to Barney. So we had the little purple Barney doll, you know, the purple dinosaur. And what we did is we attached a magnet to the top of his head and we hung him on the order of a couple meters above the ground. So, you know, on the order of 6 feet or so. And then we had uh, a projectile launcher, which is the projectile launcher we use for our projectile motion labs. And that one's basically you push a ball in with a stick, and if you push it in one click, it goes kind of slow. If you push it in two clicks, it goes a little faster. If you push it in three clicks, it goes really fast. And we could actually do it with any of those three settings, but we took the ball and we actually coated it with Velcro, the stiff feeling half of the Velcro as opposed to the soft feeling half, because Barney was plush, and if you hit him with this with the sticky stiff Velcro, it'll actually stick to the plushness. So the question is, and always is with this kind of presentation, is you know the instant that you fire this projectile. In fact, we actually had a little light gate right in front of the cannon that shot the ball. And right in front of that little cannon, there's a little light gate. And as soon as that ball blocks the light from passing, it turns the electromagnet that's holding Barney up. It turns it off. So Barney immediately falls as soon as the projectile leaves the barrel. And then you ask the students, should I shoot above Barney to account for gravity pulling down the ball? Should I shoot directly, or excuse me, should I throw the ball directly above Barney to account for the gravity pulling the ball downward as it flies? Or should I shoot directly at Barney? Or should I fire the projectile so that he can catch it, but this time actually aim it below Barney? So that's the big question. And what we're going to do is we're actually going to solve that physics problem and see what you're going to do. Does anybody have a guess as to whether you're going to aim it directly at Barney, above Barney, or below Barney? It's okay to be wrong. Remember, that's what I'm trying to teach my students. A incorrect hypothesis is a great thing. So don't worry about being wrong. So anybody have a guess on that one? Well, you
I'd
just
say at Barney.
good job. Someone said at Barney. That's a good estimate. And I will tell you, like I told you with the projectile motion problem, uh, gravity acts the same on an object whether it's been shot up, whether it's been shot down, whether it's been dropped, or whether it's been fired horizontally. And that should tell you that the gravity is going to act the same way on the projectile as it does on Barney. So let me share my screen mainly so I can stop yawning, I guess. But anyway, so I'm going to share my screen, and it's going to be my iPad. And there's a problem I wrote out again, of course. And, whoa, no, what the heck? There's a problem I wrote out in cursive, of course. And now I'm going to turn that on so you can see it. Okay. So again, you're not required to be able to read cursive, but it will help you. Hopefully, I tell you, writing in cursive is way more efficient than writing in regular letters. So I would say that alone is a really good reason to learn to write in cursive. Typing's fine, but anyways, here's what we're going to say. It says a Velcro coated ball is launched from a small launcher and is supposed to hit a plush Barney doll. However, as soon as the ball is fired at 5.00 meters per second, the doll will, that's supposed to be a W there that part of it got erased. So the doll will fall from its 3.00 meter height above the, above the end of the barrel of the launcher. If allowed to fall unmolested, Barney would land 3.50 meters to the right of the firing end of the barrel. At what angle theta should the ball be fired? So with a diagram, that'll make that a little clearer. So what I'm going to do is I'm just going to draw a little coordinate system over here. I like to think in terms of coordinates. That's not everybody's cup of tea, but I do. So what I'm saying is if I go over to here, this will be 3.50 meters, and directly above that is Barney. So here's Barney, there's his ear, there's his little spike on his head, there's his other ear, there's his eye, chubby belly, foot, little tail coming up, arm. Okay, so that's Barney. And I'm going to say Barney has a height of 3.00 meters. And I'm going to imagine further that our little launcher is actually designed to be located such that as soon as the ball fires at t equals 0, it goes right through the origin. Okay. So if you follow this, we would call that angle theta, and theta is what we want to know. What we do know is the initial velocity is 5.00 meters per second. I will tell you that I worked this during lecture today in my face-to-face class, and I did it all in terms of symbols without numbers. And the result actually comes out and is independent of the initial velocity. In fact, we tried this in my demos by firing the cannon with each of the 3 settings. And it was quite amazing because when you fire it on the shortest setting, the ball goes up, reaches its max height, and then falls. And Barney had basically been mounted to a ring stand that was mounted on a table. And then he was another 2 meters above that, like another 6 feet above that. When I shot on that slowest speed, we aimed it directly, as we learned from the physics problem, and it hit Barney not 2 seconds before, or not even a whole second before it hit the ground. So even with a really, really slow projectile, it will still hit it every time. So that's our original setup. And like I told you guys, when you're doing projectile motion, you can almost always just set up a y and a x equation of motion for the projectile. In this case, I'm going to do a y and an x for the projectile, and then a y and an x for Barney. So I'll write it over here. I'm going to say solution. Okay. And I'm going to say projectile. And then I'll say Barney. Okay. Now in the projectile, what we're going to say is x is going to be, of course, 5.00 meters per second times the cosine of theta times t. Okay. Does everybody follow how that came about? Because basically what we're using here is the equation x equals 1/2 at squared plus v0t plus x0. In the case where you have no acceleration, then the 1/2 at squared is 0, and you're left with just the v0t plus the x0. You'll notice the ball starts at x0 equals 0. So that's why this equation just has the middle term v0t. Now I'm going to call that equation 1, and actually I should probably stick with the same color I was writing it in. I'm going to call this equation 1, and then I'm going to say y is equal to negative 4.90 meters per second every second, t squared, plus 5.00 meters per second t. Notice I'm putting the t between the v0 and the sine. So that's the sine of theta right there. And then my initial height is, of course, 0. So I don't have a y0 on that one. Now, that was for the projectile, and this is equation 2. Now I have equation 1 for Barney. And equation 1 is just going to give us that x is equal to 3.50 meters, because Barney's going to fall straight down. So he's never going to move from x equal 3.50 meters until maybe the ball hits him, he catches it, and then conservation of momentum would make him fly backwards a little bit. That's about the only thing. But we're not studying it after Barney's been hit. So now I'm going to do equation 2, and equation 2 is going to be y for Barney. So y for Barney, I'm going to use the same x equals 1/2 at squared equation, but this time it's going to be y. Actually, I need a little bit more space than I laid myself, so I'm going to write it like here. This is y Barney, and that's going to be equal to negative 4.90. I'm going to leave the units off here for obvious reasons. It has 0 initial velocity, so the second term would be 0, but it does have an initial height of 3.00 meters. Okay, so that's going to be, this one would be equation 3. I don't know why I wrote 1, and this will be equation 4. So those are our equations. Does that make sense to everyone? Now remember, you can always just start with that kinematic equation, x equals 1/2 at squared plus v0t plus x0, because we're ignoring air resistance when we solve projectile motion problems. So there's no a in the x terms for the projectile, or in this case for Barney either. But there will be an a in the y terms, and whether or not you have a y0 and x0 is totally up to you. Okay. But once you have y of t, you can take the derivative of y with respect to t, and that'll give you the velocity in the vertical direction at any time. And if you take the derivative of that, that'll give you the acceleration in the vertical direction at any time. And the same thing can be done with the x of t. So basically everything you can get comes straight from that x equals 1/2 at squared plus v0t plus x0. All right, so what I'm going to do now is I am going to figure out how much time it's going to take for this projectile to get to the 3.50 meter mark. Okay, so let's do this. I'm going to say from equation 1, x equals 3.50 meters implies t equals t, what we called hang time before. It's not exactly the same thing as hang time anymore. I'm just going to say th for hit, okay? Or I could have said tc for kick, for catch. But either way, at t equals t sub h, we should get x is equal to 3.50. So with that in mind, I'm going to say 5.00 meters per second times cosine theta times th is equal to 3.50 meters. So notice this is going to give me th in terms of theta, and that's just fine. So th is going to be 3.50 meters divided by 5.00 meters per second times cosine theta in the bottom. So in principle, I could go ahead and make that a little easier and do 3.5 divided by 5. And then that number is just 0.7. So I'm going to say this is 0.7000 seconds divided by cosine theta. So you notice the meters divided by meters per second just gives us a second in the numerator. That's why I said that. I'm going to call this equation 5. And now I'm going to plug 5 into 2. So plug 5 into equation 2. And in this case, I'm going to get y is equal to negative 4.90. I'm dropping the units. We know that they work out. So 4.90 times 0.700 per cosine theta squared plus 5.00 times 0.700 over cosine theta times sine theta. So what we see here is we now have an expression for y, And it's not too bad, but I'm going to leave it like that. I'm going to call that equation 6. Now I'm going to go ahead and plug this into, I shouldn't say plug it in. I'm going to set the height of the projectile y to the height of Barney, y sub b, at that particular time. So now I'll say let y equal y for Barney at t equals th, which is equal to 0.7000 seconds over cosine theta. When I do that, what I get is negative 4.90 meters per second per second. I didn't even need to put those units. Let me ax those because they're going to be just a pain in the butt. So I'm taking equation 4 and putting 4.90 times 0.700 over cosine theta squared plus 3.00 meters. Now, this part right here that I just wrote is y Barney. And now I'm going to set that equal to just regular y, and that's negative 4.90 times 0.700 over cosine theta squared plus 5.00 times 0.700 over cosine theta times sine theta. Okay, so notice this part over here is just plain y, which came from this. Now, I think you can see that the negative 4.9 times 0.7 squared over cosine squared is on both sides of the equation. So you can just add that to both sides, and that term completely disappears. And all we're left with then is 3.00 meters. I'm putting the units back in now, is equal to 5.00 meters per second times 0.700 seconds over cosine theta times sine theta, like that. Any questions on that? Okay. So remember the 0.7 actually came from 3.5 divided by 5. So what you're going to see now is when I multiply 0.7 times 5, I get 3.50 meters. And that's just for this particular part. So I didn't want y'all to think I was talking about the denominator. So now what I have is 3.00 meters is equal to 3.50 meters. Now, sine over cosine, does anybody recall what trig function that is?
Tangent.
Yep, so that's equal to tangent theta. So we now have a result. Tangent of theta is equal to 3.00 meters divided by 3.50 meters. And if you look at the diagram, that means theta must be aimed in such a way that the thing is aimed directly at Barney. In other words, we've just proven that theta is the angle that makes that little dotted line point right to the center of Barney. So I'm going to say, boom. And notice this part is 3.50 meters. And this part, oops, that's 3.00 meters, my fault. And this part is 3. There I go again. 3.50 meters from here to here. So you can see that clearly theta, this is 3.00 meters, and this is 3.50 meters, and this is the right angle. So clearly theta is defined such that we aim it directly at Barney. So you don't aim high and you don't aim low. And whoever it was that actually guessed that, they were exactly right. Was that you, Jen? Yeah. Okay. So does that make sense to everyone? Now, you can actually do this with just using symbols like H and D. You know, you could use D for the 3.50 meters, and you could use H for the 3.00 meters, and you could just use V0 instead of 5 meters per second. And the fact that, notice the 5 meters per second completely canceled out, that tells you that it's valid for all velocities. As long as you have a velocity that's, you know, high enough for it to get there before Barney reaches the ground, you'd be good to go. Any questions on that one? Okay. So that's a little bit more difficult than the average projectile motion problem is, but I did make it a little easier by making it numerical as opposed to symbolic. So now let's go on to another example. And this is one that's very much like a problem that's at the end of your chapter in chapter 3. But I thought it was hard enough where it might be useful to show you guys how to solve it. So here's example 2. It says a hiker runs and then jumps at a 45.0-degree angle above horizontal. Assuming the ground is level and that the hiker lands 8.00 meters from where they jump, what was their initial speed when they jumped? So we basically said, hey, the runner was running at some speed. We want to know what that speed is. The runner jumps in such a way that they leave the ground at 45 degrees above horizontal, and then they land a distance 8 meters away from where they jumped. What must be that initial speed? That's part A. Part B, sometime later, the hiker finds herself on a 2.50 meter high bank next to a muddy stream 10.0 meters wide. How far short or long, that's supposed to be or, not of, or long does the hiker land if the jump was the same as in part A? In other words, assuming the same initial velocity. I don't know why that became a of instead of a R, but I'm certain it was me that did it. So I'm going to write or. Whee! Okay, does everybody sort of understand that problem? Okay, so let's draw a coordinate system just to make sure we understand the two drawings are the two scenarios. So first off, we have theta equals 45.0 degrees, and V0 is equal to question mark, and this is part A, and obviously this is our y-axis, this is our x-axis, and what we found is she landed 8.00 meters away. And then in the second part, this is X, this is Y, but now she's a good 2.5 meters above the ground. And this time she's going to fire at an angle of 45 degrees again. Oops. And that looks bad, so I'm just going to make it a little bigger so everybody can see it. 0.0 degrees. And the V0 is the same V0 we had again. And this time it's going to land right here. And we want to know, is it going to be on this side of the 10 meters, or is it going to be on that side of the 10 meters, or is it going to be right there on the 10 meters? That's part B. So does everybody understand that now? Okay. So part A is the classic, typical, whoa, somebody's trying to come in, I see, but I don't, maybe they disappeared, let's see. Oh, there it is, okay. Okay, it's the classic problem of trying to figure out what the range is. So what I'm going to say is right here is a time th, and we're going to try to find out what that is. Okay, so I'm going to again set up my equations. Let's do solution. And I'm going to use x is equal to 1/2 a t squared plus v0t plus x0. And I'm going to go ahead and write y for part A is equal to negative 4.90 t squared plus v0t cosine 45.0 degrees. And that's the whole y equation because we started it at the origin. And we're going to call that equation 1. And then the x equation, which we're going to call equation 2, the x equation is going to just be v0 times t times the sine. Oops, I wrote the sine and the cosine backwards. Mathematically, it wouldn't matter, but it's conceptually just stupid of me to do. I think it's because I was used to doing the x first, and I just instinctively wrote the x down, even though I was writing the y. So this one's going to be cosine 45.0 degrees. So I can make it even a little simpler by saying negative 4.90 t squared plus, let's say, v0 square root 2 over 2 times t. And let's say this is v0 square root 2 over 2 times t. Okay. Now, what I have to do is I have to use equation 1 and set y equal to 0 to solve for th. Okay, so the way I do that, I say negative 4.90 t squared plus v0 square root 2 over 2. Everybody knows that square root of 2 over 2 is the sine of 45 and the cosine of 45, hopefully. Times t is equal to 0. We see this is an easy one. I don't have to actually do the quadratic formula. I can just factor out a t, and what I'm going to get is 0 is equal to t times negative 4.90 t plus v0 square root 2 over 2, like that. And obviously this t that I pulled out, that's corresponds to t equals 0, so that's not very helpful. But this t that's left is going to correspond to th. So now I can say th is actually going to be equal to, notice if I put the 4.90 th, which is negative, I put it on the other side, the equal sign will become positive. So then I have to divide both sides by 4.9. So what I'm going to get is v0 square root of 2 divided by 2 times 4.9, which is 9.80. Now we already know the units are essentially meters per second every second, or meters per second squared, and we're dividing meters per second by that. So we will actually get units of time. So all the units are working out. What I'm going to do now is just do square root of 2, and I'm going to divide that by 9.80, and I'm going to turn that into a decimal, and this is going to be 0.1443 meters, or excuse me, that's just seconds. Now, I had basically 3 sig figs, so I'll underline that 3 to recommend that that's not really a sig fig. But now that I have the time, I can plug the time into x and set x equal to 8 meters. So now plug th which by the way, I'm going to go ahead and call that equation. I think I said I'm up to 2 now. Oh, that's right. That was the other one. So now this is going to be 3. So plug TH, which is given by equation 3, into 2 with X is equal to 8.00 meters. So when I do that, what I'm going to get is 8.00 is equal to V0 times 0.1443, whoa, 43 times the other part was square root of 2 over 2. So the square root of 2 over 2 is 0.707. Let's double check that. I want 4 sig figs. So I'm going to say shift square root 2 divided by 2 is equal to 0.7071. So times 0.7071 like that. So finally, we can get that V0 has to be equal to 8.00. Now I'm going to put the units in so we recognize what the unit should be. So it's 8.00 divided by 0.1443 seconds. And then 0.7071 has no units. So I'm going to say 8 divided by parenthesis 0.1443 times 0.7071, close parentheses, and this gives me 78.4. That does not seem right. Oh, that does not seem right, and here's the reason. Hold on a second. Let's not do that. I'll keep that 78.404 there. What we got to remember here is, and I didn't write it, so this is part of the problem. Notice the 0.1443 seconds. Anybody notice anything I left out of that? Notice just to the left of the equal sign, what I did was I took the square root of 2 and divided it by 9.8, but that didn't take care of the V0. The V0 is still there. So what I did was just decided that I'm going to ignore the V0, which is not a reasonable thing to do. so when I go plugging in the V0 here, I'm not actually getting V0 to be plugged in. I actually have a V0 that's still not discerned. So this is supposed to be, in fact, let's start it off from here. That 78.4 is fine. I'll just remember it later. But what we're going to do now is, remember, it's 8.00 meters is supposed to be the actual distance. And what I'm using is this equation right here, which is this right here. So this part right here is also 0.707, and this V0 is there. And then what I got to put in there is 0.1443 times V0. So the V0, that one is just right here. Everybody follow that? The V0, oops, excuse me, the V0, nope, not that one. This one. This V0 right there is that V0 right there. Now I need to multiply that by 0.7071. So I'm going to say 0.7071. That's for the square root of 2 over 2. And then I have to plug in my t, and my t is 0.1443, and that's going to be seconds times V0. So it might even help to put parentheses around that. So now you can see that V0 squared is equal to 8.00. Now I'll put in the unit meters, divided by 0.7071, which didn't have any units, times 0.1443, which has units of seconds. And of course, that's where we found 78.404 is what that equals. Anybody verify that 8 divided by 0.7071 times 0.1443? Anybody want to verify that that's 78.404 meters per second? It's actually meters squared per second squared. Just shake your head if you get it. Somebody second me on that. 78.404 roughly for the 8 divided by parenthesis 0.7071 times 1.1443.
Double checking.
Okay.
7.84.
Yep. Oh, I got 78.404. Remember, it's 8 meters divided by 0.707 times 0.1443.
Oh yeah, I got 78.4.
Okay.
I just had to enter it a couple times.
Yeah, I worked this earlier today, so I knew what the result was supposed to be. So luckily, I knew it was right. I wasn't being as arrogant as it seemed. Just assume y'all were wrong. All right, so when I take the square root, I get that I get 80 or 8.85. That might have been what you were answering a second ago, Jen. Sorry about that if that was the case, but I get 8.855. And you see that works out to be meters per second. And that's actually the answer to part A. Okay. So we've figured out that clearly we only had 3 sig figs. So I really should not be including that second 5 as a sig fig. At best, we're going to get the 8.85. I think the book, I think they did, yeah, they did exactly the same numbers, but they only used 2 sig figs in a lot of it. So they called that 8.9 meters per second. Good enough. Okay. Now that we have that, we're going to assume that the projectile is going to be fired at that same initial velocity and at that same angle, 45 degrees, but it's going to be fired from a height of 2.50 meters. So what we're going to do is figure out how far it goes by first figuring out what the time is and then multiplying that time by the horizontal component of velocity to find the distance. So the same old process that we did over and over again. Does that make sense to everyone? Any questions on that? All right, so for part B, I'm going to say y is equal to negative 4.90 t squared. This time I can say 8.85 times cosine 45 or sine 45, doesn't matter because they're both going to be the same. But that's 6.261. So I'm going to say plus 6.261. That's with one extra sig fig times t plus 2.50 meters is the initial height. Okay. I'm going to call that equation 1 for part B, and then I'm going to say x is equal to 6.261 times t. So that's going to be equation 2. What I'm going to do with equation 1 is set y equal to 0. So I'm going to say 0 is equal to negative 4.90 t squared plus 6.261 times t plus 2.50. Okay. Now that obviously begs for the quadratic formula, and that's what we're going to do. Remember, the quadratic formula says if you have a function or a equation ax squared plus bx plus c equals 0, then x is going to equal negative b plus or minus the square root of b squared minus 4 times a times c, all that divided by 2a. Now notice there's actually plus signs between the terms. So if you have any negatives, that's got to be absorbed into the a, the b, or the c. In doing that, what I get is t, whoa, I should probably mark with the marker. I'm going to get t is equal to, b is clearly 6.261, and the negative b would be negative 6.261 plus or minus the square root 6.261 squared is going to give me 39.200. And again, that's to 3 sig figs. Now minus 4 times a, which is negative. So that's going to be 4 times negative 4.9 times, and then, okay, so that's a was negative 4.9 and c is 2.50. So I've got 4 times negative 4.9 times 2.5, and that gives me negative 49 under the square root. So this will be 40. Oh, it makes positive since there was a negative already. So 49.00 is what's under the square root. And then 2 times a would be negative 9.80, like that. I can tell you if you put in the units and follow it, you'll see that the units do work out and that there's no possibility of us getting a bad answer. In fact, here's where I did it earlier. You can see the actual percentages, all the little numbers I got, and you see that I ultimately got 9.9997 meters. But notice the time I got was 1.597 seconds, or this negative amount of time. That negative amount of time is how long before 0 I would have fired the projectile from the ground height, so that when it got to the 2.50 meters height, it would have an angle of 45 degrees and be traveling at 6.261. So that's really physically what that negative 0.3194 seconds means. So it's just kind of interesting that it does that. So I'm just going to say the TH that we chose is 1.597. And I'll just tell you guys that y'all can see page 7. Whoa. Okay, so the notes are available. I'm just saying, look at page 7 if you need to see it done. Hopefully you all did it in real time while you're talking to me or while I'm talking to you, in which case you don't have to worry about it. But what I ultimately get is t equals 1.597. Yes. So t equals 1.597 seconds with 1 extra sig fig. So now that I have that, I can plug that in t, or excuse me, plug t into x, and I'll get x is equal to 6.261 meters per second. This is a bar underbar, this is reminding us that it's not a sig fig, times 1.597 seconds, again with an underbar to remind us it's not a sig fig. So I'm going to say 6.261 times 1.597, and that gives me 9.998 meters, which to 3 sig figs is clearly 10 meters on the money. So the answer is technically, it's not going to be short or long. It's right. It hits perfect. Hits perfectly. Any questions on that? Okay, so that's a slightly more difficult projectile motion problem, but it's, I think it's fairly tractable. Does anybody have any questions about that?
So that person barely made it, pretty much.
Mm-hmm. Yeah, but we thought, maybe they were going to land short, maybe they're going to land far, but it pretty much nailed it perfectly. So that's kind of interesting to know that basically the extra amount of time that you need to go 10 meters instead of 8 is exactly the amount of time it takes to fall 2.50 meters. It fired at 6.621 or 261 meters per second. Any questions? Of course, you also remember that 6.261 is the x component of velocity, and the y component would be the same. So it's not completely accurate to say that. All right, what I wanted to show you regarding the last part is relative motion. So you can imagine, for instance, here's a Mack truck. And it's carrying a flatbed trailer, say. Okay. Now this trailer comes all the way up here and runs like this. And what you see is that, let's say this is, whoa, Nelly. Let's say this is t equals 0 seconds. And then if we look at t equals 0.1 seconds, we'll get that this whole thing is now shifted like this, something like that. Okay. So in that 0.1 second, what we see is the truck went a distance of, let's say, 6 meters per second times 0.1 seconds, which is 0.6 meters. Now, if during that time, if someone was on the back and they walked a distance x equals 1.0 meters, then you'd see that since they walked in the same direction, they'd go a distance of 1.6 meters. So it seems like x should be the x of the person on the truck plus the velocity of the truck times the time. Does that make sense? Okay. Now, from that, what we can see is clearly if the truck is going, let's say 60 miles per hour on an infinitely long, infinitely flat earth, okay? And then you happen to throw a ball from the back of the truck towards the front of the truck, and you threw the ball at 40 miles per hour, again, on no air resistance, perfectly flat planet, so on and so forth. If you could really wait a whole hour, the truck would travel a distance of 60 miles because it was going 60 miles per hour. And then the ball would go 40 miles in that same hour, but that's 40 miles with respect to the spot on the back of the truck that it was on. So the truck has already moved 60 miles, so it's going to go 60 miles plus 40 miles. Does that make sense? Now that you have that, I'm going to tell you the equation. So the velocity of A with respect to C, notice how I'm reading this. The velocity of A relative to C is equal to the velocity, whoa, Lily, is equal to the velocity of A relative to B plus the velocity of B relative to C. So the key rule here for this is notice this coefficient, or excuse me, this subscript and this subscript are exactly equal to those subscripts. If you have the two subscripts on the left, being the leftmost subscript in the first symbol and the rightmost subscript in the second symbol, then you're almost there. The only other rule that we have to have is whatever this is, this has to be the same thing. So you don't have to necessarily have B there. You just have to have the same thing in both spots. So you could have Q and Q, or R and R, or in this case, B and B. Does that make sense? So when I say the velocity AB, it means the velocity of A relative to B. Okay. Now here's the neat thing. It turns out that yes, this equation is exactly right, but it also turns out that there's another rule that I think it will be obvious once I show it to you, and that is the velocity of object I as seen by object J. In other words, the velocity of I relative to J is the negative of the velocity of J relative to I. These two come together as a pair. Now, let me explain this to you. So if I'm sitting in the passenger side of a vehicle that's moving 60 miles per hour, okay, and let's say I've got one of those pivot seats so I can sit sideways, what I see is if the car in the lane next to me is going 80 miles per hour, then to me it looks like the car is going from my right to my left at 20 miles per hour. Does that make sense? Because they're going 80 and I'm going 60. So the velocity of that person, which we might call I, so the velocity of I with respect to J, which is me, is to the left, which is a negative direction, and it's 20 miles per hour. Now, if you were in the back seat of the other car, you would see me go from your right to your left, which is exactly the opposite direction that we had, because you're looking the opposite direction, so you're seeing it the opposite way. You would say that our car moves from your right to your left and therefore has a velocity of negative 20 meters per second. So if you look at this and plug in that negative with the negatives already there, you see that in fact, it's completely valid. So you would think my car is passing you going from the forward direction to the backwards direction at therefore negative 20 meters or miles per hour. And I would say it's going at positive 20 miles per hour. So that's where that comes into play. The Vij equals negative Vji. So if you ever take and need to reverse two subscripts, if you reverse them, all you got to do is change it with a negative number. Okay. Now, here's the cool part about it. We don't get to cover relativity until towards the end if we get to it all. So I will tell you that if I wanted to correct that relativistically, I would say the velocity of A as seen by C. I'd also get rid of the vector symbols because this equation only works in one dimension with relativity. So this is all moving in the x direction. It turns out the equation for relativity is still velocity of A as seen by B plus the velocity of B as seen by C, but it's got this little correction in it that is 1 plus the velocity of VAB, VBC over C squared, where C equals 299792458 0.8 meters per second, which is the speed of light. Okay. So believe it or not, that equation's not only, valid, it's only a little bit off from what relativity has. So let me show you an example with it real quick. It'll be easy peasy. Let's imagine that we have planet Earth. So here's planet Earth right here. And let's imagine that we have a spaceship A right here, and that its velocity, the velocity of A as seen by Earth, is going to be, let's say it is, let's say 18, let's say 19/20ths the speed of light. And it's going to the right, so that's by necessity positive. Okay. In other words, we all have to agree which is the positive direction, us and the other frame. So the Earth, me, which is driving ship A, thinks to the right is positive, and ship B thinks to the right is positive. So now I'm going to draw another ship. This is ship B, and the velocity of ship B as seen by Earth is actually going to be a negative. And let's say this one's even closer to the speed of light. So let's say it is 99/100ths the speed of light. Okay. What I want to know for part A is what is the velocity of B as seen by A? In other words, hey, if I'm in spacecraft A and I hold up a radar gun and I aim it at spacecraft B, what's that radar gun going to tell me how fast that thing's going? Assuming the radar gun doesn't check your own speed and correct for that and all that's just how fast is it coming towards me, right? Because it's almost like I'm sitting perfectly still and that thing's coming that fast at me, because that's what we're really trying to calculate. So let me show you how to calculate that. According to our rule, which you just learned, velocity of B as seen by A has got to be the velocity of B as seen by something plus the velocity of that something as seen by A. Well, we happen to have the velocity of A as seen by E, and we happen to have the velocity of B as seen by E. So what I'm going to do is I'm going to slip an E in here, and then that means I've got to slip an E in there. Now it fits the rule. Everybody see how it fits the rule? The outer subscripts are the same as the left-hand side, and the inner subscripts match each other. But the problem is I have VBE, but I don't have VEA. This is where we're going to use this rule. So I'm going to say this is also equal to VBE minus VAE, because I know VAE, right? So now I'm going to go ahead and plug this in. VBE is negative 99/100 times C minus positive 19/20 times C. Now, in this case, we got to get a common denominator. So the common denominator is obviously 100. So I'm going to multiply by 5/5. And I'm also going to leave that C outside. So with that in mind, I can now say negative C. Notice both of them have a negative and both have a C. So I'm just going to pull that out in front. And now 99/100 works just fine. And since I multiply 19/20 by 5/5, I can say 5 times 19, that'd be 50 plus 45. So that'd be 95. So this is going to be 95. And now they're both over 100. Does that make sense? So 99 plus 95 would be 100 plus 94. So this is negative 194 over 100 C. So that's basically 1.94 times the speed of light. And that's perfectly fine in classical physics. Now, just for the record, let's do it with relativity and see how it works. So the same equation's happening. I'm going to say relativistic. And this might be the only time we get to see any relativity, by the way. So enjoy it while you can. So we're going to say VBA is equal to VBE plus VEA over 1 plus VBE VEA over C squared. Now I'm going to make use of the negative rule. So I'm going to say VBE minus VAE over 1 minus VBE VAE over C squared again. So when I put this in, I'm going to get VBE, which was negative 99 100ths. Negative 99 over 100C minus positive 19 over 20C. And then this is all going to be divided by 1 minus 99 over 100 times 19 over 20 times C squared over C squared. And what happened there, remember, each of those had a factor of C, so I just put them off to the right and they canceled out. So the top is still going to be exactly the same answer we got before, and that answer is negative 194 over 100 C. But this part down here at the bottom is going to be, notice I've got to multiply 20 times 100. So that's going to be 2,000. And then I got to multiply 99 times 19. So I'll do that. 99 times 19 is going to give me 1,881. So 1881 over 2000. And now I have a minus sign there, but I need to get a common denominator. So I'm going to write 1 as 2,000 over 2,000. Okay. So watch what happens. This is super cool. If I take 2,000 and I subtract from it 1881, guess what you get? What? Whoa. Whoa, 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 whoa. I got 119. And I'm thinking the 119 was supposed to be the math that I got on the other one. Let's see. Normally they cancel out. That's what I'm saying. So the bottom here, I'm going to write it down just so we'll have it, is going to be 119 over 2,000. And maybe that is okay. I'm not sure. Yeah, that's okay. And the top, if we did all that right, I multiply 5 times, let's do 5 times 19 just to make sure I did that right. Ooh, 5 times 19 is 95. That's what yeah, that's what I said I had. Yeah, that's it. 95 plus 99. Okay, so this other side is going to be negative 194 over 100 times C. So what you can do now is you're going to basically take, I'll write it up here in the middle. It's going to be negative 194 over 100 times 2,000 over 119. like that. So if I do all that, I get negative 194 times 2000 divided by parentheses 100 divided by 119. No, 100 times 119. So basically, I have the 194 times 2000 over 100 times 119, close parentheses. That's going to give me, what the heck is that? 100 times 119. So this becomes 38. There's a negative here. This becomes 388,000 C over 119,000, and that has got to be wrong. I made some arithmetic error. Anybody find my arithmetic error? Crap. This always works out really nice and neatly. I don't know what happened here. I got 19 over 20. That's good. 99 over 100. That's good. When I added them, negative 99 over 100 minus 19 over 20. So that's 99 plus 95 would be 194 over 100. So that all works. And then when I said 99 times 19, that's over 2000 times 19. Anybody found any errors yet? That's 1881, and this is 2000 over 2000. So that all should have worked. Let me see if I cancel out these two zeros. That gives me 20 over 119 times 194. I'm just checking the work here. It's still giving me bigger than C. The neat thing about this denominator, which is not easy to see and it's really hard to prove, but the neat thing with that denominator is normally you end up getting exactly what you had before. But it's like in this case, we had the or the denominator was like 100 and we had 1.94 over 100 or 194 over 100. When you actually do it with the relativity formula, you'll get like 194 over 195. So that's what's supposed to happen. I don't know what happened with the arithmetic, but something went bad on that. That's all I can tell you. But those two are supposed to be multiplied down there, and 99 times 19, that all looks fine to me. I don't see anything crossing out with the 99, but there's some error. But the main thing is this formula is what you should use. Ignore the relativity part. I'm not testing you on that anyways, but I clearly made some kind of arithmetic error. In fact, when you do it, like I said, it's very normal for that kind of solution to come up with 194 over 195 or maybe 194 over 196 or something like that. That's normally what comes out. So it always turns out to be less than C, no matter how close the two of them are. And in fact, if one of them is absolutely C, it always turns out to be exactly C anyways. So that's kind of the neat thing about that. I will leave it be though. We only got 7 minutes left. Does anybody have any questions with this? Ignore the relativity thing. I thought it would be fun to do it. I don't know what happened on my error, but there's clearly something wrong. I know I'll figure it out as soon as I stop class. But this finishes chapter 3, and I wanted to go a little bit in telling you about chapter 4. But does anybody have any questions before we move on? Okay. So I normally tell a little bit of history of Newton and stuff like that when I'm introducing chapter 4, because Newton was one of the greatest minds ever lived. I mean, he's right up there with Aristotle and Einstein and Maxwell and Darwin and some of those people. These are just really upper echelon scientists that see. I've heard, for instance, one definition of a genius they often say a genius is the person that can hit the target that no one else can hit. But the response to that is even better. It says, no, a genius is the person that not only sees a target that no one else sees, and then he goes and hits it. And that's more or less like Einstein and Newton did. Okay. So in that sense, these guys are really brilliant, but it's kind of a sad story. Newton, at a young age, his uncle, who was a fairly high up person within the church community in Great Britain, and he would go see his nephew from time to time. And the mother, was okay with that. That's kind of cool. He would bring him books from Cambridge and stuff like that. And Newton really, really loved it. In fact, Newton would say, "Oh, can you get more of these or more of those?" And he really showed a good understanding of math and science. And one time the priest, who was the uncle, said, "Well, I'm not sure he's really doing anything." So he asked him about something. And darn if Newton didn't have a whole notebook compiled of all these proofs that he had done from all this math that was in these books. So he knew that Newton was the real deal, that he was actually quite brilliant. So he goes to the mother and says, "Hey, Newton's really a brilliant young man. I think he needs to go to Cambridge." She said, "Well, I can't afford Cambridge. I can't afford to, put food on the table, much less send him to college." He said, "No, no, no. I want to send him to college. I can do it with my salary. I can send him to college." And then she pursues to or presumes to start shaking him down for money. So she's sort of pimping her own son out, which is kind of ugly and disgusting in my opinion. But basically, what she says is, "Oh, I couldn't possibly work the farm without him. So there's just no way I can let him go to college." So instead of him having, X amount of dollars to send Newton to college and pay for Newton's meals and room and board, he's got, quite a bit smaller than X number of dollars, because he's got to send a fraction of that to the mom, who was just really trying to shake him down for money. Now, in her defense, she's a single mom. The dad left well before Newton was even born, so she had no other resources. So you sort of, I don't want to be completely mean, but I'm just saying that that's a possibility, that, maybe she just had to have it. She was really in a bad situation. So he sends him. But what that means is poor Newton has to go to Cambridge and has to work. And as you might guess, the job that he's given is to clean the chamber pots of the wealthy kids. So it's not cool for wealthy kids to have to go potty in the night. So it's really unfair for them to have to walk from one room to another to go to the restroom. So it's better if they kept a little fancy brass pan next to the bed, and they can just go in that, and Newton will come in the morning and clean out the poop and pee. So you can imagine he started off with a big chip on his shoulder, and he did. Okay. And he actually was quite embittered. He had a lot of things going for him, and he was very proud. He was a proud Christian. He bragged, for instance, when he was nearly 80 years old, that he was still a virgin, and that was a great, thing for him. And he was able to work more than anybody else, because he literally would work, 14, 16-hour days continuous. And sometimes he would take and, for instance, look at the sun to try to make sense of how the sun works and what the sun was producing and how the eyeball was working. What does the shape of the eyeball have to do with the vision you see, that kind of stuff. One time he stared at the sun for so long that he got such a bad case of migraines, he had to stay in his house with the blinds drawn for 3 months straight. One of the other things you can see if you look in his notebook, he basically pulled out his eyelid and took a knitting needle and jabbed it in between his eyeball and his eyelid and pried it to see if he changed the spherical shape of his eyeball, what would it look like? In other words, how would vision be affected by his eye not being perfectly spherical? When he did that, it basically, the drawing looks like a pulse of light with lightning radiating out in every direction. That's literally what he saw, and that's what he drew in his notebook. So that's exactly what you see if you actually just take and push your finger against the lower part of your eyeball with just a minor amount of pressure. You'll get that same vision. So that's some of the stuff he did that was kind of crazy. He did have, of course, enemies. He didn't like Leibniz. Leibniz and historians seem to possibly be reaching the same conclusion, that Leibniz partially stole calculus from Newton. Specifically, we know of a go-between, a person that went to see Newton, and Newton explained his system of fluxions to him. And then that person went and saw Gottfried Leibniz, and Leibniz then very shortly thereafter produces and publishes a account of calculus that's really too pretty to have been just invented. Like, it had really nice symbology for derivatives and integrals. For instance, the integral, which we all know as modern people, we know that's a infinite Riemann sum. And he used the symbol for the integral that was the elongated S, which is something that you might not have come up with when you were making it up, because you didn't know it was necessarily going to be an infinite sum of ever smaller things. So there's a lot of evidence to suggest that Newton probably did come up with it first, and history will maybe catch up with that one day. But we also found that he had a private notebook, as many scientists did. And these scientists were really weird. They were, they'd measure every ounce of poop and pee and everything that went into and out of their body to see if mass was conserved and weird stuff like that. Uh, Newton at one point says, "If I've seen further than others, it's only because I stood on the shoulders of giants." As the story is handed down, I haven't found documentation of this. We were just talking about this, me and a coworker today. As the story is handed down to us, it seems that he said that in front of the Royal Society, of which the president was a guy by the name of Robert Hooke, who was another mortal enemy of Newton. And that Robert Hooke person was probably maybe like 4'9", 4'10", something like that. So he had a bit of a short man's complex. So when he says, "If I have seen further than others, it's only because I stood on the shoulders of giants," it's really saying, "If I have seen further than others, it's only because I stood on the shoulders of giants, not hobbits like you, Mr. Hooke." So that's kind of interesting. But to be honest, Newton's first law of motion, basically saying that an object in motion tends to stay in that state of motion unless acted upon by a net external force. That is very much the same as Galileo's law of inertia. Galileo, after being threatened with the Inquisition and stuff of that sort, was put in in-house arrest, and he continued to study and produce stuff, but he just couldn't touch astronomy. So he studied kinematics and mathematics and stuff like that, and was able to discover what we now call constant velocity and constant acceleration and that sort of stuff. And he did come up with Newton's first law of motion. Newton's third law of motion: for every action, there's equal but opposite reaction. I found a notebook of Leonardo da Vinci's where he said that. He said if an eagle pushes down with a force of 100 pounds on the wind, it's obvious that the wind pushes up on the eagle with a force of 100 pounds. So in some sense, he's right when he says, "If I've stood on the shoulders of giants," that's how he got so brilliant. He's right. Really, the part that Newton completely made up for himself was Newton's second law, which basically says an object will achieve an acceleration that is directly proportional to the sum of all the forces acting on it and inversely proportional to its mass. So we'll cover that more next time. We have finished chapter 3. I'm sorry for making up the whatever problem I had in this relativistic one. I don't know what happened. Maybe I'll make one up later and do it again. But you guys are free to go. Make sure you chatted me your first and last name before you do go. But thanks for coming, everyone.
But I think
See what happens when I go and try to do something that I hadn't planned for. I make a mistake. I should probably stop doing that. See you, Jim. Hey, Mark, I found those labs. Did you see them in week? I think I put it in week 5. Did you see them?
Week 5. Let me check right now.
I will check too. It's actually supposed to be in the Canvas for your course. I'm going to go ahead and pull up Canvas for your course. And I got to make sure they're visible, so I'll do that for you as well while I'm here. So 202 is supposed to be this class. Let me do this real quick. Okay, I'm going in. I scrolled down to week 5.
I don't see week 5 on my canvas. I see week 1 and 2, but no
Oh,
week
wow.
5.
I think I put it in the wrong place. That's why. Okay, so let me do this real quick. I am going to go to another class and find where I put that, which I'm pretty sure it's 242 by mistake.
Mhm.
That was exactly what it is. Yes, okay. So what I'm going to do is I'm going to copy this to (202). And I'm going to put this in, I'm going to put it in week 2 because that's the only one that seems to be made right now. And I'm going to put it at the bottom.
Okay.
So what you're going to see pop up first is, oh crap, I don't even know why I sent that one. Ignore that one. So I'm going to pop up another one. Copy to, I have lab 4 series parallel circuits PHET final doc. That's where I'm going with it. So I'm going to send, actually, it might be easier to just email it to you. I'm going to download it first.
All right.
And okay, I did here. So we're on this one now. I'll save here. That's great. Okay, so I've got the series and parallel circuits. That's one of them. The other one is Ohm's Law PHET. So I'm going to download that one too. And I also had one that's supposed to be the electric fields. All right, so now I'm going to go back to your course. Okay. Let's see now what I can do, because that was taking too long to do it that way. And I think part of it's already in there, so that'll be kind of helpful. So down in week 2, okay, I'm going to pull up a file. The file I'm going to pull is, let's see where I'm at. There it is. Okay, there's that one. And there's this one. Okay, right there at the bottom, there should pop up 2 files in a second. One has Ohm's law in it, and the other one says series and parallel. They both have PHET. You might have to refresh your screen, but at the bottom of week 2, you'll see that now.
I found the Ohm's law, and what was the other one?
Series hyphen parallel.
Yes, series and parallel.
Yep. That's the 2 labs we did last week. And I'm looking right now for, I have a similar lab, PHET, that's for electric fields. And that's the other one that you missed. So if I can find that, I can put it here as well. I know where it is on my computer at work. There it is.
For the
Now there's
online
one. Go ahead.
for the online labs, how do I do them? Like if I don't have the equipment?
Yeah, so that PHET is a website where you can make equivalent equipment to what we have. And it's just completely electronic equipment, but you can still do the same experiments. It gives you very accurate results and stuff like that. Do you see there's 3 files down there now? The last one being electric fields and equal potentials with PHET.
Wait, let me refresh my page. What is the called? Oh wait,
Sequence 2,
say
lab 2, electric fields.
yes, electric field and equipotential W FET.
WPHET. So the PHET is a website where they've written really good computer code to behave like actual physical experimental devices. So you can go there. It tells you how to do it and all that stuff. But those that's actually 3 separate labs. The 2 we did last week are the first 2, and the one that we did for the second lab of the course is the electric fields and equal potential. So you can do all 3 of those. I'll give you I'll give you at least 3 weeks to get those done.
Okay.
If you get them done, just let me know when you turn them in. You're going to turn them in, for instance, up above where it says Lab O2 electric fields. That's where you're going to turn in the electric field one. And once I have more weeks in here, you'll see the Ohm's law and the series and parallel to turn in for probably week 4. And that's where you'll turn those in.
Okay.
Okay. Do you have any other questions?
Yes, it's homework related. So, let me show you my screen. How to show?
Yeah, let me go ahead and make sure that you can share. There you go. You should be able to share now.
So, oh, right. So, this. Oh, what's that noise?
I'm not hearing anything.
Oh, I think it's my screen. Hold up.
Okay.
There you go.
Okay.
So you say that. So this is to find V for the QCV,
Mm-hmm.
and this is the equation to find C, but like, I'm not sure like how to like cancel out the symbols because
You
this
mean like
is,
the units and stuff?
yeah,
Oh,
the units. So this is sigma naught, which is C square over N over M square,
right.
and this is 0.45 M square because I turned the centimeter square into meters, and
Okay.
this
What was
is,
the original centimeters squared? You had 45.
yes, 45 centimeters.
Oh, you're making a mistake on that one.
Oh, so just leave it as is.
Yeah, that would definitely give you you can leave it as meters, and meters is good. In fact, you need meters. The big thing is that 45.0 square centimeters, you have to multiply that by 1 meter over 100 centimeters, and then by 1 meter over 100 centimeters again. So you end up having to move the decimal 4 places to the left to
Oh,
get it in square meters. So 0.0045 exactly. So you did that. Epsilon 0 A over D, and your D is 2.45 millimeters. Yes, 0.00245. That looks good. So that should be your actual answer, 1.62 1.63 times 10 to the negative 11th. Oh, I don't know what the 1715 was for, but
so 2.788 because of 3 sig figs
okay.
times 10 to the negative 8 F. That's the unit for.
Farads
Mhm.
for EF. Oh, actually, it should be coulombs because that's a unit for charge. Q is a unit of charge, so that should be a capital C.
Oh. Oh, okay.
There you go.
Mhm. And I just have 4 more questions. Is that okay?
Okay, yeah, that's fine.
So for this one, it should be plate A has the higher potential, correct?
Electron
Because,
acquires 6.70 times 10 to the negative 16 joules of kinetic energy when it's accelerated by an electric field from plate A to plate B. So A should be the the electron actually went from A to B, and the
oh,
electrons actually go from low voltage to high voltage. So B
oh,
is
so it's B, okay.
exactly.
Mhm. And for this, I don't know, like, I'm not sure why no harm would be done because,
Let me read the question. I'm going to read the little blue box first. It says an electric field greater than about 3 million volts per meter causes air to break down. Electrons are removed from the atoms and then recombine, emitting light. If you shuffle along a carpet and then reach for a doorknob, a spark flies across a gap you estimate to be 1 millimeter between your finger and the doorknob. And of course, 1 millimeter is 1/1000th of a meter. So you get 3000 volts. That's good.
Mhm.
And so why is no harm done? And the choices are because very little charge is transferred between you and the doorknob, because there is a very large voltage because there is very little voltage because very large charge. Yeah, I would say A. What you'll learn about as we get further into electricity is that current is the thing that kills you. Okay, and it really only takes like a milliamp, but you can't deliver much charge this way with that hand shock because you're, on the order of pulling up a couple hundred electrons or maybe even a couple thousand electrons, but electrons have 10 to the negative 19th coulombs of charge. So even if you multiply that by 1,000, you still get a very, very, very small current.
Okay, so that number isn't as big as I thought.
Yeah, 3,000 volts. That's big. I mean, if you did 3,000 volts with 1 amp of current, then you could literally be exploded at that with a whole amp of current. But 3,000 volts doesn't necessarily mean you're going to get a whole amp of current. In this case, you're probably going to get less than even a milliamp, way less than a milliamp, maybe even on the order of a microamp.
Okay, so
But you're asking the right questions, so that's good. You seem to be hitting on the stuff that's sort of the most important and confusing.
okay. And for this, I don't know why, like I don't know what U is supposed to be. I know what K is.
Yeah, U is
But-
potential energy. We've been calling it PE in our class because our books, the book that you guys are using says PE, but this is one where Giancoli and the publishers use some questions from their other book where they use U for it. So that's what's coming confusing, but it's just the potential energy difference.
Any difference?
So let me read the question. It says a particle with charge of 8 times 10 to the negative 19th coulombs is placed on the x-axis in a region where the electric potential due to other charges increases in the positive x direction, but does not change in the y or z direction. And then they're asking in the first part, what is the change in potential energy UA minus UB? So you already found the change in kinetic energy, is that correct?
Yes, the kinetic energy is 1.44 times 10 to the negative 18.
And that's the change in, because that's like K final minus K initial or something like that?
Yes, that's the change in, yes, KB minus KA. So
Okay. So the change in potential energy should be the negative of that number.
the negative. Oh, you're right.
Yeah, the change in potential energy plus the change in kinetic energy is supposed to give you 0 from the chapters on conservation of energy. That's where that came from.
Okay, yeah, I think, okay, yeah, it's just been a while since I've done that chapter, so I kind of forgot, I guess.
Yeah, it was a long time ago.
All right, so the particle moved to the left with a potential difference of, so now that I know U, and I know what Q is, I believe. Yes, the particle is, so negative 1.44 times 10 made by negative 18.
Yeah, positive charges move from high voltage to low voltage, and negative charges move from low voltage to high voltage.
Well, okay, let me just apply this to this chart. So, negative charge, right? I'm just writing it down for me to later.
Okay. I just discovered a way where I can zoom into the picture you put on my screen, so I'm getting real excited.
All right, and we know Q is 8.00 times 10 is by negative 19.
Uh-huh.
So it'd be negative 1.8. And then move to the left because it's negative, right?
This was a positive particle, wasn't it? A particle with a charge of 8 times 10 to the negative 9. That's a positive charge.
Oh,
And the particle is initially at rest, is acted upon only by the electric force, and moves from point A to point B along the x-axis. So it moves from A to B.
Mhm.
So final minus initial, since it's positive, should be it should actually go to a lower voltage. So that would be negative. It should be a negative number. Yeah.
Yep.
That
But
should
does
be
it move to the left or right?
Uh, what it said up here was electric force moves from point A to point B along the x-axis, increasing in its kinetic energy. Okay, and it did say electric potential, the x-axis in a region where the electric potential due to other charges increases. So V is actually increasing from left to right.
So V is increasing from left to right, and
Uh-huh.
since it's a negative number,
So it should
that
go to the
means
right.
oh, it's going to the right.
It should be, yeah, because it's well, it increases from left to right. So no, yeah, it should go to the left. My fault. Yeah.
Okay, okay, yeah, that's what I thought. Yep, there you go.
Good job.
And this one,
Uh-huh.
I so like my thinking was C to B was the most positive because it's near is to the positive charge.
Right.
B to A is the second most positive. C to D is neutral because it's right in the middle.
Right.
Then C to E is the second most negative. Then B to A is going out. So I'm not sure if it's
Yeah, let me look up the top and see what the question was. Right here, it says using the diagrams to the left, rank each of the given paths on the basis of the charge of the change in the electric field. Okay, so they're asking how much the electric field changes. Rank the change in electric potential from positive, most positive increase in electric potential to most negative. Okay. So remember with when you're dealing with electric potential, the charge with its sign really matters. So the positive Q part is definitely the highest voltage area. So that's the one with the highest electric potential right there where the plus Q is.
Yep.
So if you go to B, that should be this the highest amongst the letters. And then A would be the second highest amongst the letters. And then C and D should be equal.
Mhm.
And then E should be the next to the lowest, and F should be the lowest.
Yep. So I guess the only place I'm confused is B to A since like would it be the most positive then since it's so close or
Remember that, yeah, remember the formula is KQ over D.
KQ over D? Mhm.
Right. So K is just a constant, but notice the distance D is very small for B. So you're going to have K times Q over a small distance. So that's going to give you a big number. And then K times Q over a bigger distance for A, that's going to give you a smaller number. So that's why B is a higher potential than A.
So would it be hmm, some would it be here?
Let's see. Most positive is from
C to B or is so because the distance between these two is so short, would this be the most positive and these two would be around here?
yeah, so B to A would be the most positive, and then B to C and B to D would be equal.
Mhm. And C to D is neutral, and C to E is second most negative, and D to F is the most negative, or
Yeah,
F
F should be
to
the most negative, yeah.
oh I mean F to E would be the most negative because it's going to Q. Alright, so oh the path from B to A and the path from F to E represent identical charges.
Changes.
Decrease in electric potential. To signify this equality, stack the cards from the two paths on top of another. So B to A and
Wait a second,
F
you got D to A and C to B. D to A and C to B are definitely different. A to C and A to D would be the same, or B to D and B to C would be the same, but not the way you have it. So
else. So C to B would be most positive, and D to A would be second most positive.
A to B should be the most positive, I think. Oh, they don't even have A to B, do they? Oh, yeah, you go.
A to B. It got B to A.
Okay, so
So
do they have B to A and A to B, or just B to A?
B to A. Oh, I think I misread that then.
So the
So
potential energy between B and A is basically it's like twice as big. So A should be half as big as the voltage at B.
Mhm.
So B to A should be the leftmost. And then you said D to C, C to D, D to A.
C to D is neutral. D,
D to A would be fine. Do you have another one with A in it? How about
no,
another
these
one?
two are the only A.
Only ones they so from D to A, uh ah, do you remember what we found the potentials to be for this is what we call electric dipole? Do you remember what we found the voltage to be? Dead
Electric.
center between them?
What did you say?
It was we did this problem in class where you had what a positive charge, positive Q, and another charge, negative Q, a certain distance apart. We found that the voltage at C and D in this diagram are actually zero. So we know that. We know B is higher than zero, and we know A is lower than B.
Uh, does it, is it like 17 point, like which problem is it? 17 point.
It was an example in the book that we did, and it should have been in chapter, I think that was chapter 17. I did it on the board the last class we met. Can I scroll up so I can see the original question on this? Okay, using diagram to the left, rank each of the given paths on the basis of the change in electric potential. So what I would do if I was you is assume a certain distance for those little squares. Assume that distance is like 1 centimeter or something,
Yes.
and assume the Q is like 100.
All right.
Okay, and then calculate the voltage at each of those points just by putting it in the formula, and use K equals 1 because it doesn't matter what K is truly equal to. So you can say, for instance, point B is 100 over 1. Point A is 100 over 2. Point C and point D are 0. That's because we've already calculated those. But you can basically see that that the effect of the negative charge and the effect of the positive charge at C and D cancel one another out. That's why you get a voltage of 0 there. If you wanted to figure out the voltage at E, that's going to be basically negative 100 over 1, and F would be negative 100 over 2. And now there's a little difference because the positive Q does some stuff to the E and F as well, just like the negative Q does some stuff to A and B, but that should get it to you close enough.
So this is B, this is A, this is E, and this is F. So B to A, and the formula for that is, what was the formula for that?
I'll tell you what, let me try something real quick.
Would it simply be 1 times 50 So b to a is 50.
Okay. Let me steal the screen from you for a second.
Okay.
Oops. Okay, there I'm ready. Let me get this right. Okay, so what I have here is A, B, C, D, E, F, and you see those charges are there, right?
Yes.
So the voltage at A is equal to K over, let's say, 2 centimeters times
Q.
positive 100
Mm-hmm.
plus K over, now I'm going to say from the negative, that's 1, 2, 3, 4, 5, 6. So that's over 6 centimeters for negative 100. So
Okay.
that's the voltage at A. And of course, we can get a common denominator by taking the K, pull it out, and ignore it. And then this would be positive 300 over 6 centimeters minus
100 over
100
6 centimeters.
over 6 centimeters. So this gives you 300 minus 100 is 200. So it's K times 200 over 6, which you can just roughly call that 200 divided by 6, and that's going to be 33.3. Now we can do VB. We can do the same thing. It's going to be K plus 100, but instead of 2 centimeters, it's going to be 1 centimeter.
Mm-hmm.
And then for the negative one, it's going to be K times negative 100. And this time it's going to be 5 because the distance is 1, 2, 3, 4, 5 squares. So that's going to be 5 centimeters. That can, again, we could just factor out that K. The least common denominator is 5. So it's going to be 500 over 5 centimeters minus 100 over 5 centimeters. So this one's going to be K times 400 over 5. And that gives us 80. Now we can do C. Now, what you can see is K is going to be plus 100, or excuse me, the part due to the positive is going to be plus 100 over. Now, it looks to me like I got 2 to the left, and from your diagram, it'd be 3 up. So it'd be 2 squared plus 3 squared square root. So this is 2 squared is 4, 3 squared is 9.
We find the
So this is the square root of
hypotenuse.
13. And the other one would be minus 100. And it should be also the square root of 13. So you can see that both of these are going to give us 0.
Yes.
And you do the VD, and you'll get the same thing,
Uh-huh.
0 again. And now we can do E. That again is going to be 100 times, or K times 100. In this case, it's going to be 1, 2, 3, 4, 5, 6. Let's see, second, 1, 2, 3, 4, 5, 6 to the E. And then plus K times negative 100 over 1 to the E. The least common denominator is 6, so that's going to be K times 600 minus 100 or excuse me, I got those backwards. It's going to be K times 100 minus 600 over 6 cm. So that one's going to be 500
over 6.
divided by 6, and that gives you what, 83?
I think your screen
And it's
stops
negative.
here. Oh, never mind.
Yeah, see, it's lower because it's negative. Now, when
Uh-huh.
you do the VF, it's the same thing. It's K times plus 100. In this case, it's 1, 2, 3, 4, 5, 6 plus K times negative 100 over 2. So this will just be K, and it'd be 100 minus 300 over 6 centimeters. So that's really negative 200 over 6.
Wait, Professor, so why is E to positive 2 6 centimeters away? I thought it was 5 centimeters.
I was trying to count it, but basically all I'm trying to do is count the distance. So this is 1, 2, 3, 4, 5. Oh, it's 5, not 6. So that was me making a boo-boo.
Okay.
And then, of course, that makes the math a little different because the least common denominator is now 5. So this would be 100 minus 500, and this would be 400 over 6. So that'd be negative 66.67. And then the other one would actually be 6 and 2, and that's negative 33. So that's supposed to be the way they're ranked, and you can see that it's just a matter of figuring out what those are. So when it says in the actual problem, when it says A to B, what you're supposed to do is the voltage of B of the second one minus the voltage of the first. So when it says letter to letter, the second letter is the final. So that's going to be the first number, and then you do minus the second number. What I just did was
Final
look up
minus
the
initial.
voltages for the points A, B, C, D, E, and F. And now you just have to do the subtraction to figure out what's what. Did you get all these figures, by the way?
Yes. Voltage for A is 33.3. Voltage
Mhm.
for B is 80. Voltage for C and D is 0. E is negative 66.67 volts. And F is negative 33.33 volts.
All right, let me stop sharing. You share yours again, and we'll look back at your results and see what you got. Okay,
So,
when it says B to A, what you want to do is the voltage of A minus the voltage of B.
so B is 80 minus 33.3.
Notice it says from B to A, so A has to be the first subtraction. You got to do the 33 minus 80.
Oh, right. Final minus initial.
Right.
33.3 minus 80. Let's see. D to A.
D to A,
So,
you see?
right here. So final, which is A. So 33.3 minus 0 is 3333. I'm just gonna put these all up.
Uh,
C to
C
D,
to, what are you doing now? C to D?
which is 0 because both of them are 0.
Exactly. 0 minus 0 equals 0.
F to E, so E, which is negative 66.67 to F, which is negative 33, so plus 33.33.
Is negative 33.3.
Yes.
And what else we got?
C to E, which is E, so negative 66.67 minus 0. C to B, So B is
80
80.
minus C is 0, so this
C.
is the 80. So far, it looks like C to B is the largest.
That sounds right.
And you did C to E, and you did C to B. Okay. So it looks like C to B is first, and then D to A is second.
D to
Yeah,
A
D to A, dog to apple.
and E to, wait, no, maybe six. Yes, E to A is
Oh, E to A. I hadn't done that one yet, have we?
oh, did we? No, I thought we did.
Did you say E is in echo or E is in boy?
Echo,
Okay, echo.
right?
Oh, C to E. We did already get that one.
Yes, C to E, which is 0, and C is negative 66.67. So that would be negative 66.67.
That looks like the smallest one so far is C to E. B to A is negative 47, so that's the next smallest so far. And then F to E
Is neutral because it's 0. Oh, no, I'm thinking of C
negative
to B.
33. Yeah. And then that was F to E. You put C to D in there by mistake, I think.
And
So now
C
we
to
have C to D, and that's the 0 one. So it should be,
neutral.
it's not exactly the same. In fact, I don't see any of them the same, but I got how many? We got 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5. I didn't get any that are equal to each other. 1, 2, 3, 4, 5, 6. C to B is 80. And then D to A is 33.
Yes.
Right. And then F to E was negative 33. The 0 should come next, I guess. So C to D should be the next one. And
F, which is negative 3.
and then after the C to D, we're at 0. So we start going into the negatives now, and the smallest negative we have is 33, and that's
Which
F to
is
E.
F to E.
And then the next smallest we got is negative
B to
47,
A,
B to A.
which is, can I do that calculation? So B is 80. No, it's uphill. So A is 33.3 minus 80, which is negative 46.7. And C to E is negative 66.67. So that's the most negative. And B to A and F to E.
Yeah, I don't think I don't see any way we made. Let me see. C to B. I'm just going to double check in my calculations. C to B, C to B, C to B, C to B. So C we found was 0, and B we found was 80. So it's 80 minus 0 is C to B. That's definitely that one. And then D to A, D was 0, and A was 33. So it's 33 minus 0. So that's certainly the second one. C to D, C was 0 and D was 0, so that's all 0. And then after C to D, we have B to A, negative 47. but we also have F to E, which is negative 33. So F to E should be the right one. And then okay, and then C to E. C would be 0 to E. E would be negative 66. So negative 66 minus 0 would be negative 66. Yeah, I would say don't want to say it can't be done because
So the correct ranking cannot be
you
determined.
you can rank them, but you just can't rank them with the number of slots they gave us. Click available hints. Let's see what it tells us. Change in the electric potential is V final minus V initial. Determine the algebraic sign. Okay. And then conceptualizing changes in electric potential for 3. So it
And
looks like
C to
everything's
B.
good there. What homework set is this, by the way?
17. Change. Wait, hold up. Oh, alright. Hold on, let me see if I can make another instance. Yes, it's change in electric potential ranking task.
Uh-huh.
That's the one we're on right now. And this is the chapter 17 homework.
This is chapter 17. Okay, I'm checking that right quick. I want to see if I'm missing anything or see if any kind of errors are up in there. So
Okay.
you said this is chapter what now?
Chapter 17.
17. Okay, I'm going to pull open that one. And it is which problem?
Change in electric potential ranking task.
Ah, gotcha. I see it. Okay. So let me pull it up on my side and see what it's saying about it. So it's saying, well, I need to look at your stuff while I'm doing this. So I'm going to pull this over here and pull that there. Okay. So your C to B is right. Your D to A is right. Your C to D is right. And it said B to A and from F to E are the same. And then it said C to E. So it's got this as what you have right now. It shows is correct.
Okay. Yep, it's correct.
But I don't know why it's saying B to A and F to E. Let me look at that diagram.
Is it
Mine.
because this is a diagram, so I guess it's because both of them are
Oh, B to A and F to E, duh. They're the same distance away from the same type. Yeah, they have to be the same. I don't even know why I didn't even notice that. Do you see why? A to B are literally one block apart, and the closest one is one block from the charge. The same thing's true about E and F. They're one block apart, and the closest one is one block from the closest charge. So yeah, they have to be the same.
okay.
Yep.
So
Is that good?
yeah, that's all my questions for now.
Okay, that's cool. I'm gonna go ahead and split so I can go get me some supper, and you have a good evening, sir.
Thank you. Have a good day
Welcome.
or
Take care.
afternoon, Professor.
No problem, Mark. Have a good one, buddy.
Thank you.
You're welcome.